Okay, in this section we want to do some examples of doing some Lewis structures in our molecular formulas. So we'll take a couple problems from the back of your book. I think this is number 4.48. And so the first one in this one, it wants us to draw the Lewis structure for N2. So remember, we said, what's the first thing that we need to do? We need to figure out how many valence electrons are needed. So the first thing we need to do is figure out how many valence electrons are needed for the atoms to reach their octet state. So we know that each of these nitrogen atoms require 8 electrons to fill their octet. Okay, so we're going to need, we've got 2 nitrogens at 8 electrons each. So we need a total of 16 electrons for both of those guys to be happy. The next thing we need to do is figure out how many they have in their valence shells, and this will help us determine how many they're going to need to share. So the next step we need to do is to determine how many they have in their valence shells. So if we look, so this was step 1. So if we look at nitrogen, we know that nitrogen on our periodic table, let's get a copy of our periodic table down here. So if we look at nitrogen, we know that it has the 2s2 and 1, 2, 3 in the p orbital. So it's got its valence shell is 5. 1, 2, 3, 4, 5. So it's got 5 electrons in its valence shell. So for 2 times the 5 electrons would show that there's 10 electrons available for the nitrogen. So this is what it wants. This is what it has so far. And so now we need to figure out how many they need to share to get there. So step 3, we have to subtract our answer for number 2 from number 1. So we need to share 6 electrons between these molecules. So you divide the number of shared electrons by 2 to determine the number of bonds that are going to be needed. So essentially you're dividing step 3 by 2. So this is essentially saying that we have 1 bond and we have 2 electrons for each bond. The electrons would cancel out and we would be left with just the number of bonds. So our molecule of nitrogen up here for N2 is going to require that we have 3 bonds that are going to be associated with it. And since there's only 2 atoms in here, we know that the nitrogen is going to have to be bonded with itself. And we know that our electron configurations, if we start drawing out our Lewis structures, they both look like this. Right? So they've got 5 electrons in there. One of those is going to be in lone pair for each of them. And the other ones have positions where they could share electrons. So each of these 3 is going to form shared pairs between the nitrogen. And this is going to end up forming a triple bond because they have to form 3 bonds to meet their octet rule. So if we draw out the Lewis structure for this guy, we would show this, each with the lone pair of electrons on it. So this is our Lewis structure for our nitrogen. So we end our calculations by determining formal charges. It's not really necessary in this case because this is the only way these guys could really bond together well. Because there's only 2 atoms that are involved in here, but we can still do this. Our formal charges are going to be number of valence electrons minus the number of non-bonded electrons plus half the number of the shared electrons. So this, you do your formal charges for each atom. So if we call this nitrogen A and nitrogen B, just for trying to separate and tell them apart from one another, we could calculate a formal charge for each of these. In this case, they both look alike, so it's going to be the same for A or B. So we could say the formal charge for nitrogen A is going to be, it's going to start with 5 electrons in its valence shell, right? And we're going to subtract off the non-bonded electrons, which is going to be 2, right, plus the electrons in the shared pair. So there's going to be 1, 2, 3 shared pairs. So that's going to be 6 electrons in the shared pairs times 1/2. So this is going to equate to 3 electrons here, plus the 2 electrons here. It's going to be a total of 5 electrons, minus the 5 electrons. So the formal charge on our nitrogens is 0. So this would represent the most structurally sound way that we could write that molecule. So these are the steps that you go through to write your chemical compound or your chemical structure for Lewis structures. So with nitrogen, it was fairly simple because it becomes obvious that you need to share 3 bonds with 2 nitrogen atoms. So this isn't the most complex one to take a look at, but as they get more complex, following these individual steps will really help you in trying to draw the correct structure for your covalent compounds. Because covalent compounds can get quite complex. Our ionic compounds are quite simple in comparison. But when we start looking at things like proteins or carbohydrates, these are really huge molecules that have many, many atoms that are involved in these bonds. So let's follow our rules again and take a look at a different compound. So I'm going to leave our rules up here so we can use them again. And let's look at another compound. Let's make it a little bit more complex. NOCl. So NOCl, we know we've got 1 atom of nitrogen. We've got 1 atom of oxygen, and we've got 1 atom of chlorine that's involved in this molecule. So if we look at the least electronegative of these atoms, I don't have the electronegativity chart right here, but if we're looking at positions on the graph, we would predict that fluorine has the highest. So oxygen and chlorine are pretty close to fluorine. These guys are going to be pretty high on electronegativity. Nitrogen is going to be the least electronegative. So this guy is going to be our volunteer for our center atom. So maybe as a pre-step, or step 1A, we have to determine the center atom. So determine center atom is the least electronegative. Okay, so that's going to be nitrogen in this case. So we're going to say nitrogen is going to be our center atom, and we're going to propose that oxygen and chlorine are going to have to come off of that guy. So now we need to determine step 1 again for this guy. How many valence electrons are needed for these atoms to reach their octet state? Each one of these guys wants to reach a total of 8. So we have 8 plus 8 plus 8 for each of the atoms involved in this molecule, or we should have a total of 24 electrons that are required to make these guys happy. Now we need to figure out how many valence electrons are available to reach this 24 electron state that we want. So we know that how many valence electrons are in nitrogen. We know nitrogen has 5 electrons. We know oxygen has 6 electrons in its valence shell. And we know that chlorine has 7 electrons in its valence shell. So these guys all added up together, they would have, what, 11, 18 electrons that they can involve in bonds to try to reach 24 electrons between them. So now we need to subtract number 2 from number 1 and see how many that have to be shared between them. So we've got 24 electrons minus our 18 electrons. This is going to be a total of, what, 6 electrons. Right? If we divide that then by 2, divide our shared electrons by 2 to determine the bonds needed. So we've got 6 electrons, essentially times 1 bond, for every 2 electrons. That's going to tell us that we need 3 bonds. So we're going to need 3 bonds to complete our molecule. And we are going to say that nitrogen is in the middle. We start then by drawing 1 bond to each atom. So we're going to draw 1 to our oxygen, 1 to our chlorine. And then we're going to add in our lone pairs, or the rest of the electrons, to the molecule. Or we can start by putting in our Lewis structures, which might be a little easier. So let's go ahead and do that. So if we position our nitrogen and our oxygen and chlorine, we know that nitrogen is going to have 5 electrons around it. And we'll put its lone pair back here. And then oxygen is going to have 6 electrons. So let's put that in blue. So we've got 4, and then they start pairing with each other. So you've got the 2 lone pair. And the chlorine has 7. We'll put that in red. So the chlorine's going to have 7. So we can see obvious places where the nitrogen and the chlorine are going to share an electron to form a bond. So here's a single bond that forms here. We can also see our nitrogen and oxygen are going to share as well. Now what we notice, once we have this structure written out, which is written here as well, we still have position on the oxygen that's not satisfied and a position on the nitrogen that's not satisfied. So these guys are going to drop down to form the double bond situation here. And so then we'll get a bond that ends up forming at that position. So that we end up forming a double bond character here. You still need to include in a Lewis structure your lone pair electrons. So you're still going to have the 3 sets of lone pair around the chlorine. And the oxygen is still going to have 2 pairs of lone pair electrons. So 1 here and 1 here. And so now we can check formal charges on our molecule and make sure that everybody is happy. So if the formal charges are 0, that's going to be the best situation that we could have. So our nitrogen in this case, whoops, nitrogen's got a lone pair too. I forgot his electrons. Right? He's still got that lone pair as well. So our nitrogen, if we determine the formal charges, we can determine them for nitrogen. This is going to equal the valence electrons, which would be 5, minus the non-bonded electrons, which would be 2 on this one. And then the bonded pairs, 1, 2, 3. So there's 6 electrons from those. And it's going to be multiplied by 1/2. We'll make those brackets here. So this one ends up being 0. The oxygen, we can see, starts off with 6 electrons in its valence shell. So we would subtract off the lone pair. There's 4 electrons in lone pairs. Plus 1/2 the bonded electrons would be 2, 4. So 4 plus 2 is 6. This is going to end up equaling 0 as well. 6 minus 6. And for the chlorine, we can calculate formal charges. Starts off with 7 electrons in its valence shell. If we subtract off the non-bonded pair is 6 electrons, plus 1/2 of the bonded electrons, which in this case is 2 electrons. We can see that this is going to equal 0 as well. 7 minus 7. So this is the ideal structure to draw this molecule in. You could draw a resonance structure that wouldn't be as likely to occur, but we could draw one where we place one of these bonds out onto the oxygen. So in this case, our nitrogen would end up looking like this, and our chlorine would end up looking like this. The oxygen, however, now has, instead of having 2 lone pairs, it's going to have 3 because it shifted that bond out there. And if we look at this molecule, the chlorine is going to be the same, but the nitrogen and the oxygen formal charges change when we have this molecule present. So I'm going to move this, our guide, and we'll calculate the formal charges for this nitrogen and this oxygen. So if our molecule looks like this, our nitrogen formal charge is going to end up having 5 valence shell electrons still, minus the non-bonding electrons, which are 2 in this case, plus 1/2 of the bonded electrons, which in this case are 1, 2. They're going to be 4 electrons involved in bonds. And so this is going to have a formal charge on it, right? Because we've got 2 electrons plus 2. So it's 5 minus 4 in this case, or a plus 1 charge. And for our oxygen, we start off with 6 valence shell electrons minus the non-bonded, which are going to be 6 electrons in this case, plus 1/2 of the bonded electrons, which is only 2 in this case. We can see that the formal charge is going to be 6 minus 7, or a minus 1 formal charge. So this one would be the preferred state, and this would be the state that our molecule is going to be most likely in most of the time. So it probably could be coerced to do this once in a while, where you can get reactivity of the molecule and have new bonds form and things like that. But you would maybe require an enzyme or other catalyst to make that go forward. Okay, so that's a second example for drawing Lewis structure. Let's do one more. So there's our key to follow again. Let's do a longer one that's a little bit harder. Okay, so when we start looking more at organic chemistry, our molecules start getting bigger. And the order that they're listed in is going to be very helpful for determining who they're bonded to. So we know that hydrogen can only form one bond by our definitions. So it's never going to be a center atom. And in this case, we've got 3 carbons, and so now carbon's not very electronegative, and so we like to nominate it for being a center atom. But what we see when we get into these more complex molecules that are much bigger and longer is that they're typically written the way that they're going to be bonded to the carbons. So when you've got 3 hydrogens here, that's saying that they're attached to that carbon when they follow that carbon in the molecular formula. This is saying that these 2 hydrogens are attached to this carbon, and this is saying that the stuff following this carbon is going to be attached to it. So that hydrogen is attached to the carbon, and the oxygen is attached to the carbon. There's also another implication when you have molecules written like this. It's indicating that these carbons are all attached to each other as well when you have a long line like this. It's saying that this carbon is also attached to this carbon, and that this carbon is attached to this carbon. So we can start generating an initial framework for our molecules as they get bigger. So we can start thinking initially, we've got a carbon bonded network that starts happening. So we know that these carbons are going to be linked together in this chain. And then this other stuff that follows the carbon is going to be attached to the carbon that comes previous to it. So we know that these 3 hydrogens have to be attached to the carbon molecule. So this is a representation of our first carbon. We also know by placement on the periodic table that carbon always wants to form 4 bonds. And so we can start keeping track of it. It also has no lone pair electrons as well, because each one of those 4 electrons that's in its valence shell wants to form a bond. So remember, our Lewis structure for carbon draws carbon with those 4 electrons in there to share. So it wants to share at every position. So when we start looking at organic compounds next term in 105, what you'll start seeing is that we can start using this counting system to keep track of our carbons and make sure that they have enough things bonded to them. So now we've got this carbon, it's got 4 bonds, it's going to be happy. This second carbon in here, which was represented here, is going to have 2 hydrogens that are also associated with it. And so it's also going to be happy, right? Because it's got 4 things that are now bonded to it. So this guy out here also has a hydrogen that's associated with it, and it's also got an oxygen that's bonded to it. Let's put that in black to designate it separate. So we know hydrogen doesn't contain any lone pairs, but we do know that oxygen does, and we can also see that this carbon's not happy like this, right? It's only got 3 bonds, 1, 2, 3. It wants a 4th one because its valence configuration looks like this. We also know that oxygen and its placement on the table, it wants to have 2 bonds that it ends up sharing as well. So right now, our carbon has an extra electron that it wants to share, and our oxygen also does. It's got those 2 lone pairs that it's got, and it also has that extra one. And so this one is going to want to come in, this one is going to want to come in, and you're going to want to form the double bond with that oxygen. So overall, this molecule, when we end up drawing it out, is going to look like this. It's going to have that double bond to the oxygen here, and then the rest of the positions will be filled up by the hydrogens. And again, we can use this kind of molecular counting system to say, okay, do all the hydrogens have single bonds? They're good. Do all the carbons have 4 bonds? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Do all of the oxygens have 2 bonds? 1, 2. So that oxygen is going to be happy. This is going to be the best Lewis structure for this molecule. So we could calculate formal charges off of this guy as well, and we would see that right now all the formal charges are going to equal 0 because everybody's happy. Everybody has their nominal amount of bonding going on to reach that octet state. When it's in this form out here, and it's only forming 1 bond, the oxygen hogs both of them and will steal them out. So they move in pairs. They usually don't move as a set of 1. But you could draw this Lewis structure a different way. If you pulled that bond out onto that oxygen, you would get formal charges on the carbon and the oxygen. The oxygen would carry the -1, the carbon would carry the +1, and that would be a less stable Lewis structure. But it would be possible. It wouldn't be as likely to occur as the structure that we have drawn here. Alright, so that represents a few different examples for drawing your Lewis structures. Ultimately, the ones that you guys will be involved in drawing now are probably going to be more simple than this one, but this is a nice example for you guys to start following and thinking about for next term. But these are the steps that you're going to take when you're determining how to draw your Lewis structure and how many bonds that you're going to need to configure within your drawing.